Let's now look into some elementary solutions to Schrodinger's wave equation. The first problem we'll discuss is the free particle in 1 dimension and 3 dimensions. Now, before going into that, let's look at the conditions for physically acceptable wave functions. So primarily, psi of x comma t has to be finite. Okay, so because we have this probability interpretation, so if it is not finite, we cannot normalize it to 1. So it has to be finite everywhere. It has to be single valued everywhere. Single valued means corresponding to every point, psi of x comma t should give you just one complex number. Corresponding to every point in space, we should get one complex number. Okay. For example, if you have a function like this, if you have some weird function like this, this cannot be a wave function, because if we take a point here, we see that the wave function, if this is the wave function, then it predicts 3 values at a particular point. All right, this is not allowed. That's what we mean when we say that it is single valued everywhere, which means that corresponding to every point in space, the wave function should return exactly one complex number. Finally, it has to be continuous everywhere in space. Okay, so if you have wave function like this, let's say that we have got a wave function like this, it has to be continuous. All right, we cannot have like this a wave function that behaves like this and then immediately makes a jump like that. All right, this is not allowed. It has to be continuous everywhere. Right, so we should, for example, if you have x-axis here, if you are talking about 1 dimension, we cannot have things like that. All right, a wave function going what do you say, jumping like that to something else. All right, this is not allowed. It has to be continuous. All right, now the derivative also has to be continuous everywhere in space. The derivative d psi by dx also has to be continuous everywhere in space. All right, there's an exception to this, except at points where the potential is infinite. So there are certain points in space where the potential can be infinite. Okay, potential can be infinite. So let's say we have got an infinite potential here. Right, in this case, the wave function has to be continuous everywhere. Wave function is always continuous everywhere. All right, we could have a wave function like this. At this point it is 0 and everywhere else it's 0. Right, so if we say that we have an infinite potential well of infinite depth, that means that the particle is trapped inside this potential well. The particle is trapped inside this potential well. It cannot go on outside. So the probability of finding the particle outside would be 0, which means that it has to be 0 at the walls also. That's the continuous. That's what we mean when we said it's continuous. All right, we cannot have a wave function like this, because outside it is 0. We see that it's not continuous. All right, a wave function like this wouldn't be continuous. All right, but the derivative, normally the derivative is continuous everywhere, but if you have an infinite potential, the derivative is allowed to be discontinuous. Okay, so we say that d psi by dx should be continuous everywhere in space except at points where the potential is infinite. All right, so for the moment, you just remember these conditions. Okay. We'll understand these things better when we discuss examples. Right, and psi of x comma t should be square integrable. Square integrable means minus infinity to infinity modulus psi of x comma t square. Modulus square of psi of x comma t integrated has to be a finite quantity. Right, now this is also important. This is also important for us to use the probability interpretation. Right, if this is not true, if this is infinite, if this integral is infinite, that means that we cannot normalize the wave function. We cannot normalize the wave function to 1. Again, then we cannot use the probability interpretation. All right, so it has to be, that's what we mean when we say that psi of x comma t has to be square integrable. So if a wave function needs to be a physically acceptable wave function, then all these conditions have to be satisfied. All right, if these conditions are not satisfied, then the function we have cannot be a physically acceptable wave function. All right, it cannot be a wave function that describes a physical system. Okay, now these conditions on physically acceptable wave functions can be used when we solve Schrodinger equation in certain cases. Especially we'll be solving Schrodinger equation with piecewise constant potentials in 1 dimension. Okay, so when we say piecewise constant potential, This means that the potential won't be a continuous function of space, all right, of coordinate. All right, we won't have potential v of x, which is a continuous function of the coordinates. Instead, we'll have the potential defined in different regions of space differently. Okay. And in such cases, we can use these boundary conditions. All right. So we can use the condition that the wave function has to be finite everywhere. We can use the condition that the wave function has to be continuous. We can use the condition that the first derivative of the wave function has to be continuous everywhere, except when there's an infinite potential, etc. All right. So basically, we'll have different potentials for different regions in space. Okay. And then we can solve the Schrodinger equation for different regions differently. Okay. We can find solutions for different regions separately. And then we can make use of the conditions that the wave function has to be continuous everywhere. Okay. So if when we go from region 1 to region 2, say, the wave function has to be continuous. The first derivative has to be continuous if this is not an infinite potential. All right. Now this information will help us to fix the solution. All right. It will help us find the solution completely. All right. So we shall be looking at such examples in the following sections. So as we said, in the case of a potential with one or more discontinuities, we don't have a single Schrodinger equation for the system, but two or more different Schrodinger equations corresponding to the different regions separated by the discontinuities. All right. So here we are talking about the discontinuities in the potential. All right. So if you have different regions in space with different potentials, all right, and if the potential is really discontinuous, and then we'll have to solve the Schrodinger equation separately for separate regions in space. Okay. So the solutions of these different Schrodinger equations give the different pieces of the wave function in the respective regions. Okay, so we can solve the Schrodinger equation in this region, we can solve it in this region, we can solve it in this region, right? And these solutions will be the different pieces of the wave functions. Okay, now using the boundary conditions, we can obtain the wave function of the system by connecting the different pieces. All right, so this is what we shall be doing. The first problem we shall discuss is that of the free particle. Now this corresponds to the simplest potential that you can imagine. It is simply V of x equal to 0, which means that the potential is 0 for any value of x. Everywhere in space, the potential is 0. Now we can write the Schrodinger equation. Okay, the Schrodinger equation becomes, you just take the Schrodinger equation and then put V equal to 0, and we get the Schrodinger equation minus h bar square divided by 2m d square psi by dx square is equal to E psi of x. Okay. Now, in fact, this is the time independent Schrodinger equation, which is the energy eigenvalue equation. Now we can write this as d square psi by dx square is equal to minus 2m by h bar square E psi of x. Okay. Now this 2m by h bar square E can be written as k square. Let's write this as k square. Okay. So this becomes the Schrodinger equation becomes d square psi by dx square is equal to minus k square E minus k square psi of x. Okay. Now we know how to solve this equation, right? We have seen such equations many times. Here we have got the second derivative of a function with respect to x, right? And we get the same function multiplied by minus k square, right? The obvious solution is of the form e raised to ikx. Okay, because if we take the derivative once, you would get ik e raised to ikx. If we take the derivative twice, you would get ik square e raised to ikx, which would be minus k square e raised to ikx. Right? So e raised to ikx obviously solves this equation. All right. Now, if e raised to ikx solves this equation, then so does e raised to minus ikx. So these are two possible solutions to the equation, which means that a linear superposition of these will also be a solution. All right. So general solution can be written as psi k of x, this k being determined by E here. Okay. All right. So if we specify k, then E is also specified. Right. So that's why we write the subscript k. So general solution is written as psi k of x equal to a plus e raised to ikx plus a minus e raised to minus ikx. All right. Here a plus and a minus are two arbitrary constants. Now we had k square is equal to 2me divided by h bar square, or E is equal to h bar square k square divided by 2m. Okay, so clearly both e raised to minus ikx and e raised to ikx are energy eigenfunctions corresponding to the energy h bar square k square divided by 2m. Right, both these are energy eigenfunctions corresponding to the same energy, same value of energy, which is given by h bar square k square divided by 2m. Now, if we have an energy eigenfunction, its time dependence is quite simple. Okay, the time dependence of an energy eigenfunction goes like exponential minus iet by h bar. Okay, so if you have an energy eigenfunction, the time dependence is given by simply multiplying the energy eigenfunction with e raised to or exponential minus iet by h bar. Okay, this we have seen several times. Okay, now if you want to include the time dependence in our solution, okay, so for example, if you have e raised to ikx, the time dependence can be introduced by multiplying this with exponential minus iet by h bar. Okay, now e by h bar can be written as omega, so this can be written as exponential ikx exponential minus I omega t. All right, the time dependence for exponential minus ikx is also the same, because both exponential minus ikx and exponential plus ikx correspond to the same energy, E is equal to h bar square k square divided by 2m. Okay, so time dependence of exponential I minus ikx is also the same. It goes as exponential minus I omega t. Okay, so the time dependence can be included and the stationary state solution can be written as, okay, or the stationary state, the wave function corresponding to stationary state can be written as a plus exponential ikx minus omega t plus a minus exponential minus ikx minus ikx plus omega t. All right, so we haven't done much here. We have taken the previous solution, that was exponential a plus exponential ikx plus a minus exponential minus ikx. All right, and we applied the time dependence in the form exponential minus I omega t. All right, and then we just combine these two terms. All right, that gives us this form of the solution. Now we can substitute for E is equal to h bar square k square divided by 2m, and then we get this form. Okay, now in this wave function we have got two terms. If you look at the first term, right, we see that the argument is kx minus omega t, and we have studied about waves and we know that this represents actually a wave that travels towards the right. Okay, similarly, this argument kx plus omega t says that this is a wave, right, or this term represents a wave that travels to the left. Okay, now the intensities of these waves are given by modulus a plus square and modulus a minus square. This is simply the amplitude squared. All right, the intensity is associated with the modulus square of the amplitude. Okay, all right. Now we may make a note that the psi plus and psi minus are actually momentum eigenfunctions. How do we check this? If we take psi plus, this is equal to a plus exponential I kx minus omega t. Okay, now if I apply the momentum operator to this, minus I h bar d by dx of psi plus, this is equal to minus I h bar from here. The derivative d by dx will pull out an ik. All right, so multiplied by ik, and then a plus e raised to ikx minus omega t. All right, so if we multiply this, it becomes h bar k plus h bar k, because there's a minus I here and a plus I here. When we multiply, we get plus. So this is plus h bar k, a plus exponential I kx minus omega t. So when we applied the momentum operator to this function, we get a constant multiplied by the same function, which means that the psi plus, okay, so what we have here is actually P acting on psi plus, momentum operator acting on psi plus, is equal to h bar k multiplied by psi plus. This is what we got. This means that psi plus is an eigen function of the momentum operator with eigenvalue plus h bar k. Okay, so this momentum is positive, right? And we have a wave traveling, so we have a particle. This represents a particle with momentum plus h bar by plus h bar k, right, which is nothing but a particle that moves towards the right because the momentum is positive. Similarly, we can see that P operator acting on psi minus is equal to minus h bar k multiplied by psi minus. Okay. In other words, psi minus is an eigenfunction of the momentum operator with eigenvalue minus h bar k. Alright, which means that the momentum is negative. In other words, this represents a particle traveling to the left. Right. Now, if the momentum is fixed for a free particle, then the energy is also fixed because the energy was simply given by h bar square k square divided by 2m, or p square divided by 2m if you like. All right. The momentum was given by, the energy was given by p square divided by 2m. Since this is a free particle, this is the total energy, the kinetic energy alone. Okay. So both these correspond to energy, the same energy, h bar square k square divided by 2m. Okay, so we can say that these psi plus and psi minus are associated with free particle traveling to the right and to the left with well-defined momenta and energy. Okay, so psi k is an energy eigenfunction. All right, this psi plus is a momentum and energy eigenfunction. Psi minus is also an eigenfunction, a simultaneous eigenfunction of the momentum and the Hamiltonian operator. Okay. Now we have found the free particle solution, the wave function corresponding to the free particle Schrodinger equation. Okay. The problem with this solution is that it does not correspond to a physical system. It's not a physically allowed wave function. Right? The wave function that we obtain for free particle is not physically allowed. What we mean is that it's not a physically allowed state of the system. Okay. For example, you could look at the probability interpretation. Right? So if we take this momentum eigenfunction e raised to I kx minus omega t, all right. Now, if this has to be a wave function, then we should be able to attach a probability interpretation to it. Okay, so let's say that psi plus is equal to, there could be some constant here, okay, a plus exponential I kx minus omega t. All right. Now, the probability interpretation says that integral psi star psi, integral minus infinity to infinity, psi star psi dx has to be equal to 1, or it has to be finite at least. It has to be finite. Okay. If this is finite, then we can normalize the wave function by dividing the wave function by the square root of this finite number. Then we can normalize the wave function. Now, normalizing the wave function is important for probability interpretation because for a normalized wave function, we would have integral minus infinity to infinity psi star psi dx equal to 1, which means that the probability, the total probability will add up to 1. Okay. But if we take this wave function, right, if we take this wave function psi plus equal to, or the momentum eigenfunction psi plus equal to a plus exponential I kx minus omega t, we see that psi plus star psi plus will become simply a plus. Okay, because this is exponential I kx minus omega t. If we take the complex conjugate, you would get exponential minus I kx minus omega t. All right, so when we multiply them, this exponential I kx minus omega t and exponential minus I kx minus omega t will multiply to 1. Okay, so we would get psi star psi is equal to a plus. Now, if we integrate this minus infinity to infinity dx, this would be simply a plus integral minus infinity to infinity dx. And we see that this is not finite. This is not finite. This is infinite. This is infinite, which means that we cannot normalize this wave function. The same is true for psi minus also. Same is true for psi minus also, right? So the wave function that we have got for the free particle is a non-normalizable wave function. It's a non-normalizable wave function. It's a non-normalizable wave function, which means that it cannot represent a physical system. It cannot represent a physical system. Okay. Now, this non-normalizability is generally solved artificially. Okay, if it is completely free, then clearly we cannot solve it. So we imagine that one way to solve the problem is to assume that the particle is actually in a box of length L. Right? So instead of being free everywhere, right, we say that it's inside a box of length L. Okay, so when we make calculations, we can assume that it's in a box of length L, and at the end of the calculation, we can take L tends to infinity. All right, and this will work when we carry out some calculations. But once we say that it's in a box of length L, all right, that means that the particle is not truly free. It's not completely free. Okay, so you cannot really call it a free particle solution. It's just an artificial fix to the issue. Okay, so let's look at this thing. Let's look at this thing called box normalization. All right. So imagining that the particle is in a box of length L. This is called as box normalization. Okay, let's see how it works. So we say integral minus infinity to plus infinity. Modulus psi square dx is equal to, we take this is limit L tends to infinity. Okay, we imagine that it's in a huge box where L tends to infinity. Okay, and instead of minus infinity to infinity, now we integrate over the width length of the box. All right, we integrate over the length of the box. So we would take this as 0, this would be minus L by 2, and this would be plus L by 2. Okay, so we integrate from minus L by 2 up to plus L by 2. All right, now we can demand that this is equal to 1. Now we can demand that this is equal to 1. All right. So for example, let's do this for psi plus. Okay, just to make it clear, let's do this for psi plus. All right, we had psi plus is equal to a plus exponential I kx minus omega t. All right, let's do this thing. We take integral minus L by 2 to L by 2. There's a modulus a plus square here, right? Modulus square of psi star psi. Okay, and then again in psi star psi this will disappear, right? When we find psi star psi, exponential I kx minus omega t and exponential minus I kx minus omega t will cancel each other. All right, and here we are simply left with dx. All right, and then if we integrate this, this is simply modulus a plus square, modulus a plus square, and dx integrated is x. Then we can apply the limit from minus L by 2 up to plus L by 2. Okay, so this will simply be equal to L. This is finite. All right, L is finite. Okay, now we don't say L is equal to L is infinite at the moment. We'll carry out the calculations assuming that it's in a box of length L. All right, in the end, we can take L tends to infinity. All right, now since this is finite, we can demand that this be equal to 1. All right, that would be the normalization. And then we get A plus is equal to 1 by square root of L. All right. Similarly, for A minus also, we'll see that it's 1 divided by square root of L. Okay. So now the normalized wave function for free particle will be taken as 1 by square root of L exponential I kx minus omega t. Okay, and 1 by psi minus would be 1 by square root of L exponential minus I kx minus omega t. Okay. Now there's another way to get around the problem. It is to adopt the delta function normalization. Okay, the delta function normalization is something that we have already seen. When we generalize from the discrete case towards a continuous case, we said that we'll normalize the eigenkets. We'll normalize the eigenkets. I think we wrote it as bra k double prime, k prime. The eigenkets of an operator with continuous eigenvalues. Okay, the eigenkets of an operator with continuous eigenvalues were normalized like this. This is delta k double prime minus k prime. Okay, we have already seen this normalization condition. This was the orthonormality relation for eigenkets of operators with continuous eigenvalues. Okay, now if you want to talk about k instead of k double prime and k prime, we can talk also about k and L, and then we can write bra k ket L is equal to delta k minus L. Okay, now if these were discrete, we could write it as delta KL, where delta KL is the Kronecker delta. Okay. So we said that the generalization of this would be delta K minus L. All right. Now what we have here is the position space representation of this relation, the position space or the coordinate space representation of this relation. Okay. So bra K would be represented by psi star K of X. Okay. And ket L would be represented by psi L of X. All right, and then we say that this is equal to delta K minus L. All right, of course, you know how to go from here to here. We just introduce the completeness relation. We introduce the identity operator in terms of the completeness relation of the position eigencase. We know how to do this. Okay, so once we do that, we'll get this relation, and this is known as the Dirac delta function normalization or the delta function normalization. Now let's try this for this case. All right, let's demand that this wave function. Okay, let me just drop this plus and minus. I'll just work with plus. So let me say psi k is equal to exponential. Okay, we had an a plus exponential I kx minus omega t. Okay, so psi star k would be a plus star exponential minus I kx minus omega t. All right. Similarly, we can write psi L as a plus exponential I. Here would be Lx minus omega t. All right, we just put an L instead of a k over here. Okay, here it's a k, here it's a L. All right. Now let's find psi star k psi L first. This would be modulus a plus square. So now if you look at this exponential minus I omega t here, right, will cancel with the exponential minus I minus omega t in this term. So that term will just drop out. Right, we are left with exponential. I can be pulled outside here. I write it like this, exponential I. Okay, and here there is an L. I think I'll pull the x also outside. Here there is an x. Here also there is an x. All right, and then we are left with L minus k exponential modulus a plus square exponential I x L minus k. Okay, now we integrate this from minus infinity to infinity. All right, so this would become integrating from minus infinity to infinity. This would become, let's say, integral psi star psi dx from minus infinity to infinity would become modulus a plus square and integral minus infinity to infinity exponential I x L minus k dx. All right. Now we know that this is related to the integral representation of the Dirac delta function. This is something that we have already discussed. Right? This is related to the integral representation of the Dirac delta function. Because we know that if you have something like integral minus infinity to infinity exponential I x k minus L dx, this is equal to 2 pi delta k minus L. Okay, this is something that you have to remember. If you don't know this already, just take this opportunity to memorize this. All right, this is an important representation of the Dirac delta. Okay, this means that integral minus infinity to infinity modulus a plus square psi k star psi L dx is equal to, we get this as modulus a plus square 2 pi delta k minus L. Okay, now we demand that this is equal to delta k minus L. Right, we demand that this is equal to delta k minus L. So the question is, what's the value of a plus in such a way that this integral is delta k minus L? Now it's clearly it's clear how to do this now. All right, so we now demand that this is equal to delta k minus L, which means that a plus square has to be equal to 1 divided by 2 pi. Right? Then this modulus a plus square would cancel with this 2 pi. Right? Or we can write a plus is equal to 1 divided by square root of 2 pi. Right? There could be a pure phase factor which is of no consequence. Right? So we can write a plus equal to 1 divided by square root of 2 pi. Now if we choose a plus equal to 1 divided by square root of 2 pi, then this relation would be satisfied. This relation would be satisfied. Okay. If this relation is satisfied, then we can still make it workable. Right? We can carry out calculations using this. It all works well. Okay. Right, so this is known as the Dirac delta normalization. So in the Dirac delta normalization, we'll say that psi plus of x, let's say psi plus k of x is equal to, this would be 1 divided by square root of 2 pi exponential I kx minus omega t. Okay, if you also want the time dependence, that is. Okay. Similarly, you can write it down for psi minus also, right? This would be the correct normalization factor in this case, right? Now, in the former case was that we assumed that the particle is in a box, right? But if you make that assumption, the particle is not quite free. Okay. Now, if you adopt the Dirac delta normalization, the integral is not exactly unity. It's not unity. It's clearly not unity, right? It is true that if k is not equal to L, this is 0. But when k is equal to L, this is not equal to 1, right? So the Kronecker delta was fine over there. But in this case, when k is equal to L, the Dirac delta is not equal to 1. So integral is not exactly unity, right? Now this makes it mathematically workable. Either the box normalization or the Dirac delta function normalization makes it useful, right? We can use these things, right? But still, these do not represent a physical state of a system. Okay, it could be an idealization. Now, the second problem is that these functions that we obtained, they do not satisfy the uncertainty relationship. Okay, because these wave functions are definite momentum states. These are definite momentum states. We saw that these are momentum eigenfunctions. These are definite momentum states. So in these states, right, in psi plus and psi minus, in these states, uncertainty in momentum is 0 because these are the momentum eigenstates. Okay. Because obviously momentum eigenstates are states with definite value for the momentum, which means that the uncertainty is 0. You could also try calculating and see that the uncertainty is actually equal to 0. Okay. Now, if the uncertainty relationship we wrote was something like this: delta p square delta x square was greater than or equal to h bar square divided by 4. Okay. Now this relation wouldn't be satisfied if delta p is equal to 0. Right. This relation won't be satisfied if delta p is equal to 0. All right. But any physical state of a quantum mechanical system has to conform to the uncertainty relationship. Right. That means that psi plus minus k of x cannot represent the physical state of a particle. It cannot represent the physical state of a particle. Okay. Now we can try to construct a wave function which satisfies the uncertainty relationship. Right? How do we do this? We can combine momentum eigenfunctions. We can take a superposition of the momentum eigenfunctions and try to construct a wave function that satisfies the uncertainty relationship. All right. Now, if we can do this, and if we do this, we find that we get a wave packet. Right? We get a wave packet which is no more an eigenstate of the momentum operator. Right? So this wave packet would be consistent with the uncertainty relation, but it won't be an eigenstate of the momentum operator. Okay. Now, if you think about this, the momentum eigenstate is the plane wave, as we said. Right. So if we plot the real part alone, it would be something like this. Of course, the imaginary part is also there. Okay. Now, just by looking at this and thinking about the probability amplitudes, this seems to suggest that the probability amplitude for finding the position, right, finding the particle at any point in space, it's all equal. It's everywhere equal. All right, of course, because there's also the complex part which we have not plotted here. Right, if we plot the other part also, then that would mean that the probability amplitude for measuring the position of the particle would be the same everywhere in space, which means that the position is completely uncertain. All right, so you can also say that if you are in a momentum eigenstate, that's the state of definite momentum, the position would become completely uncertain. All right. In other words, all right, another way of saying is this thing is that a single particle, all right, you should think of it as existing everywhere in space, right? But of course, we shouldn't go to such extremes because this is not what do you say, a physically allowed state, all right? Nor is it normalizable, so we cannot really use the probability interpretation there, right? But we are just trying to uh, get some understanding, right, of this particular wave function. These difficulties with regard to the concept of the free particle probably indicate that we cannot carry over to the domain of quantum mechanics the classical concept of the particle. Okay, so we have a classical concept of a particle. We can think of a point particle in classical mechanics, right? But we cannot take that idea directly to quantum mechanics because in quantum mechanics things behave differently. Of course, if it was a classical mechanical particle, then we wouldn't have an interference pattern as we discussed in the case of interference of electrons. Okay. So this means that the concept of a classical particle cannot be entirely taken into the realm of quantum mechanics. All right. But still we can think of a quantum mechanical particle, for example, the electron as a particle which has a definite mass, electric charge and spin. You can think of a particle as something with a definite mass, electric charge, spin, etc. This is fine. This we are allowed to do, right? But we cannot assume at the same time that it has a definite momentum or a definite trajectory. So you really cannot think of the particle as following a particular trajectory or a particular path, right? You also should not think of the particle as having a definite position in space, definite location in space. Okay? These things are not allowed in quantum mechanics. Okay, so the best we can do in quantum mechanics is that we can associate a wave function with the particle. That's what we actually do. We associate a wave function to the particle, right? And what does wave function do? The wave function gives us the probability. Actually, it's the probability amplitude for finding the particle at any point in space. That's the best we can do, right? So the wave function associates a complex number to every point in space, to every possible point in space. Okay, this is the best we can do. We cannot really think of the particle as having a definite momentum or a definite position or a definite trajectory, etc. Right? Such visualizations are wrong. So the best we can do is to associate with the particle in quantum mechanics a wave function or a state vector, okay, which conforms to both the probability interpretation and the uncertainty relationship. So when we assign a wave function to a particle, or a state vector to a particle, it should be in such a way that the uncertainty relationship is respected, as well as the wave function has to be normalizable. It has to be a physical wave function. All right. It is the state or the wave function which determines what values, if at all, of energy, momentum, etc., the particle can take on. Right. So once you have the wave function, that's all the information that we have. All right. It will tell us the possible energy values the particle can take, the possible momenta the particle can take. If you make a measurement, what are the possible values of energy, momenta, etc. What are the probabilities for finding these values in these measurements? Okay. All these things, all this information is contained in the wave function. All right. So that's the best thing that we can do about a quantum mechanical particle. Okay. Now, even though the free particle that we discussed is not a proper quantum mechanical system, it's not an allowed quantum mechanical system, but still we can use it as a calculational tool or as an idealized object. Now, this thing we have already done in classical mechanics. Okay, for example, even in classical mechanics, the concept of a free particle, a point particle, it's an idealization. Right? The concept of a point particle is an idealization. All right, but still, it's still consistent with the laws of mechanics, and we can use this for calculations. Okay. In the same way, we can use these idealized objects called momentum eigenfunction or position eigenfunction, etc. when we make calculations. We can use it as a calculational tool. Right? There's no problem in using it as a calculational tool. Right? The only problem is that it does not represent a physical object as such. Okay, but these are quite useful. We can still use the momentum eigenfunctions as the basis, the momentum eigenvectors as the basis vectors. We could use the position eigenvectors as the basis vectors. Of course, we already used these things. Okay. The free particle solution can be directly generalized to 3 dimensions. All right. So in the delta function normalization, we can write psi k vector of r vector. All right. Since we are in 3 dimensions, these become vectors. This is a momentum. This is associated with the momentum vector. This is the position vector. Okay, and in the delta function normalization, instead of 1 by square root of 2 pi, we would have 1 by 2 pi raised to 3 by 2, because there would be 1 divided by square root of 2 pi for each dimension in space. Right? So you would have the normalization constant as 1 by 2 pi raised to 3 by 2. All right, and instead of e raised to ikx, obviously we would have e raised to ik vector dot r vector, right, or exponential ik vector dot r vector. Now, if you are talking about box normalization, then you should assume that it is in the 3-dimensional box of volume V. Okay, and then the normalization factor would become 1 divided by V whole raised to 1 by 2. Okay, now if you take V as L cube, then this would be 1 by, the normalization factor would be 1 divided by L raised to 3 by 2. All right. Now, we see that since there are no boundary conditions, right, there are no boundary conditions being imposed on the wave functions, on the free particle wave functions, we see that k is equal to modulus of k vector, right? This can take any values from 0 to infinity, okay, or the momentum can take any values between 0 to infinity. In other words, the energy can take any value between 0 and infinity. Okay, which means that the energy spectrum is continuous. For a free particle, the energy spectrum is continuous. Okay, so the quantization of these energies, which you might already be familiar with, these appear when the system is actually bound, right? When there are certain boundary conditions imposed. In that case, this energy spectrum will become discrete. Okay, but for free particle, right? For free particle, this energy, momentum, all these are continuous. Right? We have continuous energy spectrum. In the next example, we'll see the case of a bound state, and we'll see that for bound states, if you are in a bound state, the Schrodinger equation says that then the energy spectrum will be discrete. We shall be seeing this in the next example when we discuss the infinite well problem. Okay, we have discussed the free particle problem. Okay, this corresponds to V equal to 0. So we substituted V equal to 0 in the time independent Schrodinger equation. And we found that the energy eigenfunctions are plane waves, exponential ikx and exponential minus ikx. Right? Both these can be solutions to the time independent Schrodinger equation with V equal to 0. Okay, so a linear combination also would be a solution. Right? So we wrote down the stationary state. Now these states are special. These are called plane waves. Okay, these are momentum eigenfunctions. Both these momentum eigenfunctions. All right. So exponential ikx is the momentum eigenfunction with eigenvalue plus h bar k, and exponential minus ikx is the momentum eigenfunction with momentum eigenvalue minus h bar k. The energy eigenvalues are simply h bar square k square divided by 2m. Okay. Now the momentum, there is no restriction on the values that the momentum can take. Okay. So similarly, there is no restriction on the values that energy can take. So we have a continuous spectrum. We have a continuous spectrum. All right. But later we'll see that if there is boundary conditions, if there are boundary conditions, then the energy spectrum will become discrete. Okay. Now, specifically, if the particle is somehow bound, if it's a bound state, then we'll see that the energy eigenvalues will become discrete. Right. In this case, we have got a continuous spectrum. Okay. So with that, we'll conclude the discussion of the free particle. In the next class, we'll discuss the infinite well potential.